This is Senior Math Challenge 2022. This was only a couple of days ago. Usual disclaimers apply. The mark scheme isn't released, so I don't know for sure that this is all correct. I haven't even checked over it that thoroughly, to be honest. I certainly haven't done any optimization of any problem. So these are just the solutions that I came up with the first time I did it. I haven't really fixed anything at all. So anyway, with that out of the way, let's make a start. There are probably better ways to do this. Like I just said, optimizing with problems is something that I'll leave you to do. But as soon as I saw this, I just thought difference of two squares. So this is 2 minus 1 into 2 plus 1. This is 3 minus 1 into 3 plus 1, and so on. When you work out what those things are, you get this, and then just a load of stuff cancels. In fact, it all cancels except for one of the ones on top and the 5 on bottom, and you get 1/5. Good. Question number 2. What is the smallest prime? So these have to be prime. This one isn't because it's 3 times 13. What is the smallest actual prime? I think all of these are. That's the sum of 5 different primes. If you add up the 5 smallest primes, not including 2, because I noticed all of these are odd, which means if I use 2, I'll have 2 and then 4 other odd numbers, which will make an even in total. So I don't want to use 2, but I can use those to get 39, which is one of these, but it's not prime. So okay, well, can I make 40? Well, I can't. If I increase any of these by 2, I'll just hit the next prime, or I'll hit 9, which isn't prime. Or I hit 15, which isn't prime, so I have to increase this one by 4, and I can make 43, and that would be an acceptable solution. Number 3, just look at it, mate. There's 1, 2, 3, 4, and then 5 and 6, so I think there are 6. Good. Question number 4, so this square has area 4, because it's side length 2, the total thing is 25. 25 minus 4 gives you 21, halve that to get 10.5, and so the ratio is 4 to 10.5, doubled is 8 to 21. Nice. Question number 5. So we don't like fractions, we don't like decimals in fractions, so just times this one by 100 and times this one by 10 to make this. But then notice that 100 101ths plus 1 101th is 101 101ths, and so is 10 11ths plus 1 11th, that's 11 11ths. But this is just 1 plus 1 plus 1, and so the answer is 3. Good. Question number 6, I mean, very straightforward. This is 2 squared, this is 2 cubed. Follow your indices laws, this is 2 to the 1600, this is 2 to the 1200, take them away, 2 to the 400 will be the answer. Excellent. Question number 7. There's probably a more intelligent way to do this. I just listed multiples of 85 for a bit, and then I noticed I had 2 that were quite nice, so I was keeping my eye on those. List multiples of 66, and eventually you get to here, and you notice, oh, well, that one and that one make a nice round £5, so I can choose this one and this one. I think that seems like the lowest thing I can do, and I'll have 7 stamps in total, 5 of these and 2 of those, and we'll have the answer. Number 8. There must be an easier way of doing this, I think. What I said was that this is obviously 90. Interior angle of a hexagon is 120, so this is 30. But of course, all of these are completely symmetrical and congruent, so this is also 30 here. And then, of course, 120 minus 30 gives you 60 here. But of course, you can repeat that argument all the way around, right? So 30, this is 120, which makes this 60 because it's on a straight line. And eventually you work out that these are definitely equilateral triangles. And even more than that, it means this length, because that's part of this equilateral triangle, and all the equilateral triangles are congruent, is the same as this length, which is the same as this length. So what I decided to say was, well, okay, this is also a regular hexagon, therefore, because all these lengths are the same. So I'm looking for a scale factor from this hexagon to the smaller one. So if I call maybe this length x, I can say, well, this length here is x over 2, because you can see I've split it in half there. And then I can work out that, okay, well, cos of 30 is x over 2 over the hypotenuse, and the hypotenuse is the side length of the hexagon that I'm trying to find. So cos of 30 equals this over that. I'll call it y. Cos of 30 is root 3 over 2. Do some cross multiplying, whatever. Eventually you get y is x over root 3. So we have an original hexagon length x, and this hexagon has side length x over root 3, so the scale factor is 1 over root 3. And that's in terms of length. So the scale factor in area is 1 over root 3 squared, which is 1 over 3. So the scale factor from this area to the smaller area is a third, so we just divide that by 3 and we get 72. There must be an easier way to do that. You can write in how I was supposed to find that. But anyway, so a billionth of a second is 1 times 10 to the minus 9. So you do this divided by 1 times 10 to the 9, I guess is another way of saying that. Of course, 3 divided by 1 is 3. This is 3 to the power 10 times 10 to the power minus 1, which is 0.3, which is 30 centimeters, because that was all in meters, of course. Question 10, the easiest question on the paper for sure. Just multiply that over there. When you expand out, you notice the 3x squareds cancel immediately, and we just get a nice linear equation. The answer is -2. Question 11. So this one, I mean, I've said this I think before in previous math challenges. You should always go into the math challenge knowing the prime factorization of whatever year it is that you're doing. So I knew going into this that 2022 is 2 times 3 times 337. So okay, you can just say it's 2 times 1011 though. You don't even need to know that much. Now two things that multiply to make 2. Well, the only options are 1 and 2, right? But you can't put a 2 here because then you can't multiply a 2 with an integer to make that. So the 2 must be here and the 1 must be here, and then this must be 1011. And then you think, okay, but what if I had chosen different things to put here? And it turns out it doesn't matter, right? If you would just use the 2 and the 3 here and the 337 there. Again, because 6 doesn't share any factors with this because it's prime, the 1 must go down here, and the 6 must there, and the 337 there. And no matter how you do this, you're always going to end up with n as 1. Because the 3 prime factors of 2022 obviously don't share any primes themselves, and so whatever you choose here must leave your 1 here. This one here, so I think there's probably a couple of ways to do this, but automatically, just on autopilot, this is a square number, take away another square number. That's the difference of 2 squares. So it's this one, take away this one, times this one, plus this one. And when you do this, you get something quite nice, because timesing by this number isn't that bad. You just times by a billion, I think. Is it a billion? Or whatever the extra one with the zeros is. You just times by that, and then take away 1 copy of this. So of course, this times by that is this. Take away 1 copy of this, just do a column, right? Now, of course, this is a bit complicated because you can't take any of these zeros away, so you have to get rid of one of those from there and donate this to give this a 1. But then you have to start from the scratch again and go to here until you can get rid of this to make a 9 and give this to the 1, but then you do it again and eventually get rid of all these. They all turned into 9s, except for the very first one, which keeps it because it doesn't have to give anything to another digit because it's the last one. This makes a 7, and you get a bunch of 6s, you make a 2 here, and then a bunch of 3s, and you just count up the sum of these. So this is, I think, 6 3s, that's 18, you got 2 here, you got 6 6s, that's 36, and then a 7 there, add those together, you get 63. So quite an interesting question. I think there are other ways to do it, but on autopilot, I just immediately did that. Anyway, 3 rugs, so there's the 3 rugs, have a combined area of 90. We're looking to set them out area 60, so we need an overlap of 30 in total. Now, we've already got 12 meters of overlap from the doubled up sort of section, so we need 18 more meters squared of overlap. But the thing is, when you overlap 3 rugs, you waste 2 rugs rather than just 1. So like this 12 meters of overlap here, that's only wasting 1 rug's worth of 12 meters. Whereas when you have 3 rugs over the top of each other, you waste 2 rugs. So if you're looking for 18 meters squared more of overlap, you actually only need 9 meters squared. There's actually that triple overlap because you waste 9 from, say, the orange rug and then 9 from the see-through one as well. So that gives you 18. So just 9 meters of triple overlap will do it, and you have the answer. Number 14 then. So the classic Mr. Drew math challenge things, just make up a number. Call this length 3 because then I can split it into the ratio 1 to 2 very easily, 1 and 2. Do some Pythagoras here. This is 2 as well because this is, oh my gosh, that should be a 2. That's frustrating. I'm just going to fix that and hope that there's no more mistakes here and just be okay with it. So that should be a 2. Pythagoras says 1 squared plus 2 squared is root 5. But then, okay, this is root 5 here. Like all of this is root 5, I should say. And you're supposed to split this also in the ratio 2 to 1, but that's not very nice. So what I'm going to do is I'm going to triple the original number that I chose. If I make that a 9, that makes this a 3 and a 6, and that makes this a 6. And then 3 squared plus 6 squared square rooted is 3 root 5, because I've just multiplied the previous triangle by 3. Right, it's 3, 6, 3 root 5. But I can split 3 root 5 really nicely. That's 2 root 5 and root 5. So the root 5 is also here. And then when you square that out, you get 5 plus 4 times 5, which is 20. So that's 25. Rooted is 5. And so the area of this is 25. The area of this is 81, because I chose a 9 here. So it's 25 over 81. 15, getting into the second section of the paper, really. First 15, second 15. So we have a race that's 100 meters long. The hare gets to the end, while the tortoise is only 25 meters in. So what that means is that the tortoise has a speed of s, the hare has a speed of 4s. So basically, every 4 meters the hare covers, the tortoise covers 1 meter. That's how I'm thinking about this. And of course, now there are 75 meters to go between them as the hare turns around. And the hare's going to travel, again, 4 times as far as the tortoise did. So that's a ratio of 4 to 1, so there's 5 parts. So just do 75 remaining meters into 5, gives you that the hare is going to go 4 times this, which is 60, and the tortoise is going to go 15 in that time. Just double check everything. This adds up to 75, which adds that to make 100. This distance is still 4 times this distance, which is good because that was the original ratio, and we have a distance of 60 apart. 60 from the finish line where they meet again. So this question is quite good. Root 0 plus root 0 is not 1, so it can't be D. It doesn't go through the origin. This is clearly the graph x plus y equals 1, because it's just a straight line rearranged as y equals minus x plus 1, so it can't be that. So we're left with these three. Now this looks a lot to me like x squared plus y squared equals 1, if you complete it around into a nice circle, so it's definitely not that either. Left with these two, but of course, if you were to swap the x and the y inputs to make this root y plus root x equals 1, that's just the same statement, because it doesn't matter which order you add. And what that means is, if you reflect it in the line y equals x, it's the same graph. But of course, this doesn't, so there's the line y equals x. This is not reflective in y equals x, so that one's discarded. Another justification you could give instead is that, okay, just plug in a number for y that's quite close to 1. Like clearly this is the point 1, 0, when you've got root 0 plus root 1 equals 1. But plug in a number that's quite close, like 0.81. That's not even that close, but sure. Root that is 0.9, obviously. And so then we have root x plus 0.9 equals 1, rearrange and square out, and you get x as a very small number. So we're clearly this graph, because as we approach y equals 1, x becomes very, very small. Okay, so yeah, that would be our answer definitely for B. Excellent. So this one is possible to cheat very quickly on. What it's talking about is that the octagon looks like this, and you've cut out 6 triangles. Now each triangle has side length 1, they're equilateral, so we can work out the area of this by just doing 1 times sine 60 times a half, and there's 4 of them. Of course, sine 60 is root 3 over 2, and then the 2's cancel and you get root 3. So we're going to do the area of the octagon. This shaded area is the area of the octagon minus root 3. Now, if you look at the answers, only 3 of them have a minus root 3. The other 2 have positives. So unless the area of the octagon has both root 2's and root 3's in it, the answer must be B, E, or D. So I'm just going to say it's that. But then you look more closely at this. 2 minus 2 root 2 is negative, and minus root 3 is definitely even more negative. So this is a completely ridiculous answer. But also this is, right? Root 2 is about 1.4 times 2 is 2.8. So this is also a negative answer. So we can pretty quickly jump to the answer of B just by working out the triangles. Now, if you want to work out the area of the hexagon, you can do, the octagon, you can do. There's lots of ways to do it. I don't even think this is the best way, but if you complete a square around this, like so, you have that this is an isosceles right-angled triangle, and this hypotenuse here is 1, because of course it's a regular hexagon, so all of octagon, so that all this is 1. That means this is 1 over root 2, because this squared is a half plus this half equals 1 squared. And so the side of this imaginary square going all the way around is 1 over root 2 plus 1 over root 2, which is 2 over 2 root 2 plus 1. And I can just square that to find the area of this, and then take away these 4 triangles that I created, which is just a half times 1 over root 2 times 1 over root 2. And there's 4 of those. And if you work through the maths here, this all cancels to make 1. This you square out, this is just root 2. You square it out, and you eventually get this, which is what I said it would be. There's lots of easier ways, I think, to work out octagons, but that's just what I did. That should totally say octagon as well. I'm confused as to why I wrote that down. Okay, number 8, Ian. So, just set 3 to the x equals big X, 3 to y equals big Y. This, you should spot this is 3 to the y times 3 to the 1, because then you add the indices. So this is just 3 to the big Y, so that's just this. So that expression is that. This one I do a very similar thing. Times this one by 3. Take away. Divide by 8, and you get this. I know this is blasphemous for me to write something like this with a decimal, but you'll see why I'm doing it. If I put it back into here, 3 root 3 take away 1.5 root 3 is 1.5 root 3, and then you just divide by 3 to get 0.5 root 3. So that's x and y, and of course this is just big X and big Y. So we add these together, and we get 2 root 3 in total. 19, so this is a really nice question. I'd made a Tamura video on this semi-recently. How many solutions? You're always thinking about graph sketching. So let's sketch this graph, rearrange it to make it this. That's very easy to sketch. Quadratic move down 2022 units. Its roots are, of course, going to be roots 2022 and negative as well. Okay, so that's our graph. What about this one? Well, you could rearrange it to make this, and if you know to square root and do a plus minus root this, if you know how to sketch that, then great. If you don't, there's a cheat here, which is just rearrange it differently to make this. And now I can sketch this straight away, because notice how this is exactly the same as this, except the x and the y are swapped. So if I just put the x-axis here and the y-axis here, this graph must now just look the same as this one did. Because, I mean, it doesn't matter what we label things, what letters we use, right? Like if this letter here means this is that letter's axis and it looks like this, then this must be the same. But of course, now what I have to do is kind of, I'll turn it 90 degrees to the side to make it look like this, and then I'll flip it over to make it look like this. Of course, the graph doesn't change when I flip it over like that. And now, of course, I've got it in the right orientation, so I can just put it over here. Notice how, because this is minus 2022, it's further across than this one was. And likewise, its root is at root 2022, so that's further up than this one was, and we have 1, 2, 3, 4 solutions. Quite a nice problem. Again, you could have just square rooted this and know what the plus minus square root graph looks like, and then translated it this many places left. That also gets you it immediately. But this is a nice trick to know, I guess, in the future. Okay, so this is a circle with radius 10. Let's call the side length of the square x. And this is an isosceles right angled triangle again. So the same Pythagoras that we did before tells us that this is x over root 2, and so is this, because squaring this you get x squared over 2, plus x squared over 2 is x squared, which is this side squared. Good. Now I can draw a line down to this part, which is also length 10, because that's the radius of the circle again. And now this is 90 and this is 45, so this whole angle is 135, and I'm not too happy about this method, but I can do cosine rule here. 10 squared equals x squared plus x over root 2 squared minus 2 times this times that times cos of 135. And you do need to know what cos of 135 is for this method to work, so there's probably another way of doing it. But cos of 135, if you draw the graph, it's 45 degrees on from 90, cos goes into the negative, it kind of dips down into negatives after 90, so this is minus 1 over root 2. Everything else kind of just ends up being quite nice. These cancel for a 2, cancel with that, these become a plus. You add these together, you times by 2, divide by 5, and we get x squared is 40, which of course is the area of the square. Perfect. So this question here, I was very confused by this for a few seconds when I first saw it. If you draw a horizontal line through there, that's clearly one of the semicircles they're talking about, which has diameter 2, and this is a straight edge they're talking about, which also has diameter 2. Now they're talking about another semicircle. Where is that? Well, it's not vertical. The hint was that they have horizontal diameters, so the other ones don't, maybe. That's what they're implying. And eventually you notice that this diagonal there makes a nice semicircle up here. And of course, Pythagoras 2 squared plus 2 squared rooted is 2 root 2. So this has diameter 2 root 2, and that's the semicircle. Now, I'm not really sure why they gave you 2 of these, because you can just halve it down, focus on this area, and times the answers by 2. So, okay, how do we find this area then? Well, let's do this big semicircle, the area of that. So that's going to be half times half of this squared times pi, because this is the diameter, so it's going to be root 2 squared times pi. And then if I have that semicircle, I add this triangle, and then take away the smaller semicircle, I think I'll end up with this area, and then times it by 2. So big semicircle is a half of this squared times pi. Triangle is a half times 2 times 2. That, by the way, that makes a 2, cancels with that, makes a pi. This makes 2. And small semicircle has radius 1, so it's a half times 1 squared times pi, which is pi over 2. This is just going to be pi over 2 plus 2, and then times the answer by 2 to get pi plus 4. 22, a nice question here. You don't like roots within roots, so maybe the best idea would be square both sides here to get this. The square obviously cancels the square root on this side. Now you do just want to be careful when you do that, because if you have this equation obviously has one solution, which is x equals 5. If you square it, suddenly you have 2 solutions to your problem. X can be either 5 or minus 5 to make this work. So you just need to be a bit careful when you square to then check at the end that your answers do actually work, because you might have created some fake solutions. So okay, I'll check that at the end, but for now, let's expand this out. That squared is 8, take away 4 lots of this y, and then plus a y squared. And now, it's possible to get stuck a bit here without knowing what to do. What I did was I put this all underneath one surd. So I said this is root 16, this is root 2, and this is root y squared. And then I put them all together to make this. Now, why am I doing that? Well, x and y have to be integers, right? So if this side is to equal this side, then this surd here must be equivalent to this surd here. And the non-surds must also be equivalent to each other. So we can just compare the surds and the non-surds. So x plus 23 must equal 32y squared, and x must equal 8 plus y squared. Because x and y are integers, there's no way to make these surds, right? So there's no way to interfere to get the surds otherwise. So the surds must equal the surds, and likewise. So of course here we can just square up both sides again, or just compare what's underneath. I don't need to be so concerned about inventing solutions there, I don't think, but maybe we'll check at the end anyway as well. Of course we can just substitute this x into there, and we can solve that, and we'll get y is plus or minus 1. And when we put that into here, we get, plus or minus 1 squared is 1, so that makes x equal to 9. Now the problem here, and this is why we need to check, is simply to say there are two solutions, 9, 1 and 9 minus 1, except if you put in 9 into this left-hand side, you're going to get some number. I don't really care what it is, but that number cannot be equal to both 2 root 2 plus 1 and 2 root 2 minus 1. Right? It can only be equal to one of those things. So there's only one solution here. I actually haven't even bothered to check which one it is, but I know there's only one. It's either 9, 1 or 9 minus 1. I don't care which. It's one of the two. Good. Question 23. So this area is 90, which means the sides are root 90, which you can simplify to be 9 times 10, so it's 3 root 10. This is root 10, which makes this length 2 root 10 by doing 3 root 10 minus root 10. And now, of course, this length is root 10 as well, so you can use Pythagoras here. This makes this squared is 10, this squared is 50, so this is going to be root 60, which, this root is 10, this is squared is 10, this squared is 4 times 10, which is 40, so this is root 50, which is 25 times 2, which is 5 root 2. Okay, now over here, this is 2 root 10. In fact, I've gone over here first. These two triangles are clearly similar because corresponding angles, here and here, both 90 degrees. So this is root 10, which means this little triangle is half of this one. So this little length here is root 10 over 2, and this hypotenuse here is 5 over 2 root 2. Okay, good. Now going over here, this is clearly 2 root 10 because it's root 40. So that makes this root 10 here, because of 3 root 10 minus this one makes root 10. This is clearly 2 root 10 again because it's part of the square. So this hypotenuse is the same as this one, 5 root 2. That's going to be very helpful to notice in a second. We can then scale factor here because this is 2 root 10. These triangles are clearly similar because of all corresponding angles. So if this is 2 root 10 here, it's double this one, so that's 4 root 10 down there, and this is 10 root 2 over there. Okay, now for the last triangle up at the top here. Now if this angle was x and this angle was y, x plus y are clearly 90 because this angle is 90. This is x because they're corresponding. This is y, which makes this x because this is a 90 here. X plus y must make 90, which we know they do, so this must be x. And now what about these two angles here? Well, this is where we notice that this triangle here is congruent to this one because we've got the 3 same sides. So the angles must be the same because they're congruent, and so the y in between root 10 and 5 root 2 must also be here, and so the x must be over here. But again, this makes this one y because of the 90 degrees there, which makes that angle 90 degrees there. And that's all I need really, because now I can just say, well, I just need this length times by this length divided by 2. Will give me my answer for the area of the whole triangle. So I just need these two lengths, but that's very simple to work out because I know we've still got similar triangles here. So this is the hardest bit, but the scale factor from this triangle to this triangle, the hypotenuse is this and this. So we will say the scale factor is this divided by this. So we need to do this side times this scale factor to get over here, and this side times this to get over here. You can do both of those things. This obviously simplifies because this is root 2, root 5. Root 2's cancel. So it's going to be this times this is that. This times this, the root, what's the easiest way to do that? Again, that's root 5, root 2. Root 5 times root 5 is 5, cancels with that, so it's 3 times root 2. And then likewise over here, you're going to get a similar thing. It's just twice this one, isn't it, because of the double here. And now all of this length here is 3 plus 5 plus 2.5, which is 10.5 root 2. All of this is 21 root 2. Do this times a half, and eventually you get, well, these make a 2, cancels with that, 21 times 21 over 2. The only possible solution is the one with the 0.5. You could have noticed at the start, actually, that like this triangle has to be bigger than 150, we could say, because of these boxes. That's nowhere near 150 because that's about 3. So this clearly is nowhere near 150, nor is that. This seems way too big. And so actually you probably had a 50-50 guess within a few seconds of looking at the answers, if you had noticed. So now we get to the point in the challenge where I basically blown through those first 23 questions, although I understand there were probably mistakes in there, and you'll tell me about those in the comments. I was feeling pretty good about myself, and then I looked at this question and 25 as well, and I just and this is where this question was hard, and so was 25. This one took me a while. As soon as I read this question, I thought it piqued my interest because I've never seen a question like it. And so it's fun when I never see questions that I haven't seen before, because I have to figure out actually what to do rather than just remember similar things that I've seen. So, okay, what did I do here? Well, it's talking about a maximum, when y takes maximum possible value. So if we think about a graph of this, we're looking for some kind of maximum point and asking what value of y that is, what value of x that is, and then just doing the y minus the x in terms of p and q, obviously. So, okay, well, how do you find a maximum of a graph? Well, the obvious answer in sixth form is to differentiate. And at this point, I just want to make a quick public service announcement, which is that in Senior Math Challenge, differentiation is never the answer. It's never helpful. It's certainly not ever the actual thing that you have to do, but it's also never even a helpful thing to do. They just never write questions where differentiation is necessary. So if you are ever feeling like you need to differentiate in a math challenge, perhaps go talk to someone who's perhaps been in a similar situation before, and hopefully you'll figure out a solution together. So, okay, so I differentiated this, and I could implicitly differentiate, but I had actually already rearranged for y because that felt like quite a natural thing to do. So I rearranged for y, and I won't do this on screen, but you can differentiate this with either product rule or quotient rule. I'm a product rule person, so I did that. If you do that, and I won't show it on screen, if you do that though, and then set it to 0 because we're looking for a turning point, you get PQ equals 0. And that's a problem for a couple of reasons. It's a problem because it doesn't tell you anything about x and y, which is what I was really looking for. And it's also a problem because p and q are positive constants, so PQ cannot be equal to 0, which implies that this graph does not have a turning point. Which is confusing because if it doesn't have a turning point, how does y have a maximum possible value? Like, this graph doesn't have a turning point, and clearly y just goes up forever, so like, how does it have a maximum? And then I was thinking about it for a bit, and I was like, well, hang on. If I'm thinking about what this graph could possibly look like to give me a maximum, why am I not just sketching what this graph looks like rather than thinking about hypothetical graphs? So, okay, I sketched what this graph looks like, and as soon as I thought that, it kind of all clicked, because if you don't know, when you see a term like this on the bottom, if x is equal to q, then you're dividing by 0, which means there's an asymptote. You can't do that, obviously, so there's an asymptote at x equals q, which is a vertical line at q. So this graph has an asymptote here somewhere, again, q being positive and constant. Okay, so what happens when this graph approaches this line then? Well, if you approach it from the right, imagine x was just a tiny bit bigger than q. You'd have some positive number on the top, and then you'd have maybe, like, imagine q was 5 and x was 5.01. Then on the bottom you'd have 0.01, and when you divide by that you make a really big number. So this is approaching this asymptote from this side here. And the closer you get to q, the bigger the number is going to be, because you're dividing by a smaller and smaller number. Now on the other side, when x is slightly less than q, like 4.99, you're dividing by a very small negative number. So the answer is going to be very big, but it's going to be negative. So again, you approach it from the other side like this. So okay, that's why it doesn't have a maximum, because it shoots up like this and then shoots up down from down here like this, a bit like the tan graph. So okay, how does y possibly have a maximum then? Well, that's when you remember the last piece of the puzzle, which is that this is not a normal graph. In fact, it's not a graph at all, because x and y can only be integers. So this is not a graph, it's just a collection of coordinates at the integer inputs, giving you integer outputs. So actually, the biggest y can be is when x, because q is a positive constant that's an integer, the biggest that y can be is when x is just q plus 1. Like you just choose the next input you can, which is possibly here, and that's the biggest y will ever be. You can't be any bigger because you can't choose a number for x closer to q than q plus 1, because we're all integers here. So okay, you put that x value into here, and you find q is this, and then all you have to do is do y minus x, which is that. Expand out, you can factorize, and you get this one here. Quite an interesting question. I don't know whether that's the intended solution. There's probably other things you can do. But anyway, question 25. Sorry about that click there. I just dropped something. So question 25. So, okay, this question, I had no idea what to do for a while. So I actually had a mathematical friend send me in a solution that I really liked. So I'm just going to use that. the area of a pyramid like this is a third times base times perpendicular height. It doesn't matter that it's not symmetrical like this. This is just always the formula that works for the volume. I said area before. It's volume, of course. Now, the base of this is fairly easy to work out. It's going to be 10 and 10 and 4 here. So we can draw a line down here, make a length of 2 there, and do 10 squared minus 2 squared is root 96, which has a factor of 16 in it, I believe, so it's 4 root 6. So the area of this base is 4 times a half times this. The 4's make 16 times a half is 8. So yeah, 8 root 6. So that's the base. Good. So the base is there. The third we just need the perpendicular height, which is this length. And this is where I got stuck, because I couldn't work out to find this length. Now, when you drop down like this, you're going to meet the line down the middle of that base, this same line here. And we need to work out this length here, of course. Now, we know this distance here is 4. It's 4 there. And this is 4 root 6, as we've already decided. Now, I could express this height in terms of theta if I called this angle theta. This is obviously 4 sine theta, because sine theta is this over that, so times by 4 and you get this. So this is 4 sine theta. So okay, I've shifted the problem now to, I don't just need to find this length. If I could just find theta, then I could put it into this length, and I would be fine. I would just put it there and I'd have my answer. So is there a way to find theta? Well, this triangle isn't helpful because I don't have enough information. This length isn't very helpful because it's not really making a triangle with theta. I guess I could go down there. Maybe I should have thought about that. But what I actually did was I went across like this. Actually, no, I did think about going down like this. But then you're missing some angles, and it's still very difficult to work out. In fact, though, sine rule, thinking about it, sine rule might work. Yeah, draw a line up to here, and then maybe try some sine rule. That might work. But an easier way is to draw a line across like this, making a 90-degree angle here. And then you can say, well, this is just length 2. And this thing here, we can work out because it's 4, this is the hypotenuse because that's the right angle there, 4 root 6 all squared minus 2 squared. Well, 4 root 6 squared is 96. So minus 2 squared is 94. 92. And so this is root 92. And so sine theta, again, because this is a right angle, sine theta is opposite over hypotenuse. So sine theta is root 92 over 4 root 6. That cancels to this, by the way, because it's 4 times 23. And sine theta is this over that, which makes this. But now, of course, I can just put that 4 sine theta. I can times it by 4, and just that's the height. Like this times 4 is just the height there. This cancels, but times it by 4, and we get the height, right? Because that's 4 sine theta. And now I've got a third times this. And of course, the root 6's cancel. 4 over 2 is 2 times 8 is 16. Divide by 3, and we get 16 divided by 3, root 23. That's the entire challenge. Thank you so much for watching. Hope I didn't make too many mistakes. But yeah, see you next time.